Okay. So I'm very happy today to introduce Professor Paulo Farinas for this week's QFI seminar. So Professor Farinas got his bachelor's degree from the Federal University of São Carlos in 1990. And he got his master's degree from São Carlos in 1992. During his PhD, he was at Los Alamos from 1993 to 1995. And then he was at São Carlos again from 1995 to 1997. He was a postdoc at Boston College from 1997 to 1998, and he was a postdoc at the Institute of Physics Gilbert at the State University of Campinas in Campinas, Brazil, from 1998 to 2000. From 2000 to 2002, he was a young researcher. He had a young researcher grant at the Sao Paulo Research Foundation. From 2002 to 2008, he was associate professor at the Institute of Physics at Rio de Janeiro, Brazil. And from 2008 to present day, he is professor of physics at São Carlos University in São Carlos, Brazil. So please help me in welcoming either by unmuting yourself or virtually Professor Paulo Farinas.
Okay, thank you for this long introduction. I should thank Joshua for the opportunity and also for the initiative. And all of the attendants and our viewers, in particular Kevin, who was my thesis advisor or co-advisor when I stayed in Los Alamos for a while. And well, this is the title of my talk. And part of the results I will comment on here are from Henrique's thesis. Henrique Bentham. And recently he spent some time with the Department of Physics at PCD during his PhD. So some of you may have met him, and he's also in the attendance. Now, in the late 60s, Leggett and Rice published their work accounting for the effects of helium-3 interactions on spin diffusion, what has become known as the Leggett-Rice effect. The results, whose implications were experimentally confirmed, come from the modification of the simple Fick-like diffusion. This is the Fick-like diffusion. And if you do some Fermi liquid calculation, you obtain what is called the Leggett-Rice constant term, which is a precessional term, and it modifies the Fick dynamics, the Fick's law. So the G became known as the Leggett-Rice parameter. More recently, I've been seeing some of the cold atom community calling it G, the Leggett-Rice parameter. So this correction describes the precession of the spin current above the local magnetization. So when G is equal to 0, this term disappears, right? So if you put the interactions to 0, you will have no such an effect, all right? However, this is not a two ways relation, right? You can have strongly interacting fermions with G equal to 0. So more recent accounts related to the existence of this precessional term advanced some results in condensed matter physics, like in this recent collaborative effort. So this precessional term has a relation to a amplitude mode, which has a role in this collaborative effort. Just to show an example of some consequences besides, of course, the Leggett-Rice effect itself. Now, today, I base this presentation on a not so recent result, which, however, illustrates well the idea of two quantum fluids not in isolation. So here is the outline of the talk. I will go through the outline by giving some preview of the ideas. I will start with the basic idea of splitting a more complex system into simpler ones, Then I'll try very briefly to expand on what I mean when I say spin textures. Next, I will cover some of the essentials in Fermi liquids, putting some emphasis on the kinetic equation of motions, which would be this lower part here. And finally, I will briefly show some results on transport of electrons through spin textures in ferromagnetic metals. So, the two-fluid idea. Here we have two quantum fluids in isolation. You have an interacting complex system, and you imagine it can be described by some idealized systems whose direct combination provide at least an approximate description of your observations. Now, in order to include the often important effects of interactions, you think of a third term to couple the two model systems. Both systems may be interacting themselves, so that's why I call them fluids, maybe. Now, of course, I have a particular choice in mind for these systems, a Fermi liquid coupled to a spin texture. So this is the quantum fluids not in isolation. So I mean to describe the dynamics of both the texture and transport electrons in a separate way by splitting them. So this idea is neither new nor uncommon. Here we see a paper from Akiezer and Pomeranchuk, where they refer to this idea in 1959 to address the possibility of a pairing of electrons in a weak ferromagnet. It makes reference to what can be thought of as two bands, an S band and a D band, each of them having electrons with different behaviors. You see here in yellow, when they explicitly refer to S electrons and D electrons. And they are splitting a ferromagnetic system as a whole in these two so-called bands. Now note that if the real interacting system is ferromagnetic metal, then its paramagnetic component, which is the one to the left here, it's possibly better described by a nearly ferromagnetic Fermi liquid. The reason being that in the real system, conducting and ferromagnetic electrons are not distinct. I'll come back to this soon, but now I'll review quite briefly some of the essentials of the Fermi liquid theory, which are suitable for this proposal. Now, I believe this looks familiar to more than half of the audience, I would bet. So I'll not go through all the details of, what things are which, etc. It's just looking a little bit at this slide to recall what basic Fermi liquid theory is about, with all the assumptions here. So from expanding the energy, the ground state energy, as a function of the distribution functions, and having a cutoff in momentum in space are essential ingredients for what the theory differentiates the theory from other approaches. These are usual practical aspects of Landau Fermi liquid theory. The spherical Fermi surfaces, mapping all states of a complicated Fermi surface into a sphere with equal volume. This is Luttinger. There's no strict necessity for a spherical Fermi surface, but one assumes sufficient symmetry and smoothness to allow expansion of the interaction at the Fermi surface. In this rectangle here, you have some known realizations in metals, helium-3, and heavy fermions. Other examples are listed here, where Fermi liquid theories play important roles. Some traditional examples, others more recent. So you have normal interacting fermions and ferromagnetic metals, spin orbit magnets, nematic phase unitary Fermi gases. And the advantage of these theories is that they provide you access to instabilities through Pomerantchuk conditions, for example, and collective modes like famous zero sound and paramagnetic spin waves, etc. Now, two basic ingredients I'd like to be standing out for this particular talk is that equations of motion are written for distribution functions, which introduces a momentum space constraint, a cutoff in the Fermi momentum. So it leads to a Wigner-Boltzmann-Slim scheme. Many of you may have come in touch with. And the interaction between fermions is written as an energy function, as I said before, near the Fermi momentum, which yields a reasonable low number of parameters. Now, how do we obtain kinetic equations? So, of course, I want to spare you of the derivation. Some of the derivation, though, is important because in this derivation, we understand where the precessional Leggettwise term I mentioned in the first slides originates from, and how the resultant dynamics differs from usual block-like dynamics. But I will avoid most of the details in the next few slides, since they are somewhat standard. So we start with the equal time propagator for the interacting fermions and do some transformation Weil and Wigner transformations. And I'm doing this for paramagnetic Fermi liquids. Some of you will notice from the notation that I'm using, because it is, again, very standard material. And I believe these slides will be available with the recorded video, so it refers to standard material. We often start from some place after, like block equations or some ready-to-use kinetic equation, because, of course, we do not want to run the standard model from the beginning every time we need to calculate something. So without pointing any details, again, I got already to the semi-classical equation of motion for a distribution matrix, which is the equation at the bottom of the slide here. I dropped all the indices for simplicity. Now, with some choices for the distributions, which are quite general, we can see here that the precession of quantum hydrodynamics, the so-called hydrodynamics for the precessional mode that I mentioned, is in connection to a correction, which is first ordered in the h-bar constant, in the Planck's constant. So this is a semi-classical approach, although the Boltzmann-like approach for a distribution that has a cutoff in Fermi momentum is also not completely classical, right? Just the dynamics. So this represented local spin density and magnetic field, including the contribution from interactions here. You see the possible external magnetic field and the interaction here. Am I on? Yeah, I think
yeah,
okay.
Yeah.
All right. Yeah, I saw some changes. I thought there might be some problems. I just go on. Now here, we then take the traces, define the local spin density and the spin current for solving the result, then solving the resulting coupled equations. We find that the steady state solution satisfies the extended fixed loss, the precessional term I mentioned before, that gives rise to the Leggettwise effect in helium-3. So this is the scheme in the paramagnetic side, and some of you are maybe bored. Why is this guy presenting such a traditional 60-year-old things, right? But it'll make clear that we'll avoid to make calculations in the ferromagnetic case, which make things even more confusing. So here at this scenario of the paramagnetic case, can you see a nice decoupling for this paramagnetic case? Can you, is this Fermi liquid really isolated? That's my question. And to answer this, we go back to this derivation slides and clean it up a bit. So there it is. You see that the external magnetic field is coupled to the Fermi liquid in an SD fashion, I would say, which is disturbed here, right? It comes right from the handling of the, but this is an external magnetic field, right? So our quantum fluid is not totally isolated. Yeah, indeed, you have a quantum fluid in a magnetic field here. If you want to study both systems dynamically, you use Maxwell equations on the right side, right? So that's what we did with another box. Instead of having a simple magnetic field here, we'll think of a weak ferromagnetic as the whole system, and then split it as S electrons and S band electrons and D band electrons. So, and we derive the kinetic equations in the pretty much the same way as we do in the paramagnetic side. But now the dynamics on the right side, on the texture side, is given by some other, usually classical, giving the conditions for, low energy and long wavelength excitations. This is quite traditional stuff, which is called sometimes the Landau-Lifshitz-Gilbert approach. And the coupling brings up a torque, which is called spin transfer torque, which is intrinsic, in comparison to other torques that may exist in such non-homogeneous systems. So some features that I will point out, the paramagnetic X-band becomes very similar to helium-3, since the coupling to the magnetization does not include the Lorentz force that distinguishes charged fermions from the uncharged ones. So this is a plus for us, because you can be filling in the helium-3 landscape even more. The Lorentz force would contribute from very, I was suspected to contribute very, very, very small, local field proportional to V over C kind of term. So now, spin textures can be fabricated. I should say something about spin textures here, which will be very brief. They can be fabricated with increasing control in nanowires, layers, and other nanostructures. They became promising for the use of fast-track memories with possible increases of order of magnitude in the reading and the writing processes. The electric current density introduces an intrinsic torque, which I mentioned on the texture, called spin transfer torque. So some desirable features are here for the members. The low critical electronic currents and higher domain wall velocities. So it's interesting to calculate this in the view of some correlation introduced by the Fermi liquid, right? Let me go back to these, because someone would ask, well, the density of electrons in these currents, they are usually very low. So interaction may be disregard, some second, third order effect. So why do you consider that? Well, the reason I already gave, the electrons, as soon as they enter the metal, they're not distinct from the ferromagnetic metal. So they will carry some of the correlations that are sustaining the ferromagnetic state. So it's quite reasonable to assume that it actually will be not a block-like dynamics, but some more correlated dynamics that is given exactly from the handling of Fermi liquid theory on the left side of my plot there. So here are the results. So I don't need to go through what I did, because it's already there in the paramagnetic case, most of it. There are some details. There are spin flip terms, which are extra, come from impurities and other external influences. So I will spare you of all of this. I will point just for the electric current term, that is just an additional term to the spin current. And this is the result. You have in green here, in this ball is the difference. The rest of it is all block dynamics. So this large term here is the correction. And for those of you who already studied Leggett-Wright's effect, this will look familiar, okay? But besides those additions, you have also renormalizations. What you do in the end, we implement the ferromagnetic, the quasi-ferromagnetic or nearly ferromagnetic condition, which is approaching one of the Landau parameters to -1, right? And then the typical length of the textures must be greater than the length scale associated with the dynamics, whose result is on the right side of this inequality here. Okay, so this is the scale that you obtain from calculations, either with or without Fermi liquid corrections. And then you compare to the typical path. So the spin textures path must be larger, much larger than this guy here, in order for the description to be valid. But then notice, if you go to a nearly ferromagnetic Fermi liquid, this becomes arbitrary. So it might explain some of the experimental observations that this approach, the block approach, works pretty fine and quite abrupt in homogeneities. So people, as far as I know, maybe they have other explanations for this, because I didn't know in the time I did this calculations. All right. So this is the main result that I would like to talk to you about. Now I'm already began to summarize by talking a little bit more about other experimental results, but that are not still. I'm not very confident about them yet. So this is Enrique Bertrand thesis results. He calculated the critical currents and domain-wall velocities in his thesis, which he finished in 2018. And while we've been able to correct some numerical values for domain-wide velocities, the critical currents obtained were still too large. The same problem block-like dynamics suffered from. Right? We did not have the opportunity to make a more comprehensive study looking for consistency, and because there are many parameters, both in block dynamics and in the one that consider Fermi liquids. So as usual, the inclusion of Fermi liquid effects introduced yet at least a couple of independent parameters. And it's not a surprise that we can reproduce some of the results better. So if you have more parameters, it's not a surprise. So I believe there are more aspects to be explored within Fermi liquid approach, and I'm thinking about some of them right now. I'm willing to come back to this old, already 12 years old stuff of mine. So thanks.
Okay, so if anyone has any questions, you can either raise your hand or you can just unmute yourself and ask your question. So I think I have a question. So what do you expect the end result for this calculation should be? Basically, what do you expect, what new physics will you gain from applying Fermi liquid theory to these systems as opposed to some other approach?
Well, I don't think I gained any new physics in this work that I did, but I was, well, I don't mean to be too pushy about this, but it reminds me of the Sommerfeld gas, because people didn't know why it works so well, and then Fermi liquid can explain some of the factors that are missing. And then this did the same, in my opinion, but which are much more complicated dynamics. And so actually it didn't gain much physics. Then we invested in the applied part, trying to see if we recovered the correct experimental values and corrected some of the things that the block dynamics can't get numerically. And this is in part a lot of work from Enrique digging out experimental. As you know, this area of spin transfer torques is quite promising and high stakes, so lots of experiments and the difficulties. So the plain answer to your question is no new physics here, right? There's some new understanding, right? Mm-hmm. That's my thought on your question. Did I get your question right?
Yeah, I mean, maybe in a way, couldn't this lead just say some novel application, say spintronics?
Oh, this is a consequence of the area, right? Mm-hmm. The context, not. Mm-hmm. Again, I say I was able, in my opinion, to understand some things that worked before, and as far as I know, people didn't understand why they did. And then we tried to apply it to see if we could recover some of the things that were not working, but we didn't manage to do that. So that's the state of affairs right now.
Okay. Okay, so any other questions that anybody has? Like I said, please unmute yourself and just ask them. So maybe I'll wait 5 or 6 seconds in case anybody wants to ask any lingering questions. Okay. So maybe let's thank Paulo again.